Well, behold, this is lecture 13 of the mechanical vibrations course in summer of 2024. And what I have on the agenda today is indicated here. We want to talk about measurement devices and specifically something called seismometer and then accelerometer. This course is not about experimentation and experimental techniques, etc. But these two particular items, namely seismometer and accelerometer, use some of the design and analysis techniques that we have learned in the first 6 weeks of the course. This is why we're going to go through them. Okay. So it is actually the discussion about both of these gadgets is a direct application of forced harmonic response and base excitation that we covered 2 weeks ago. Okay. First thing that you should know is that when you talk about a transducer, and that's a common term in engineering, what it's really referring to is a device that changes mechanical motion, such as displacement, for example, into a voltage, or the other way around. So transducer is the piece of equipment responsible for changing mechanical motion into voltage. What I'm showing you on the left side is a very old-fashioned rudimentary accelerometer. Okay. Now notice that what it is a casing, and inside of that casing, which is mounted on a base, inside of that casing there is a mass, spring, and a damper. And because you're dealing with electrical reading, there is a voltage source. For example, we can think about this thing as a battery, hypothetical battery, okay? Now, this gadget is mounted on a base where we want to actually record the motion of the space, either in the form of displacement or, I mean, down the road, of course, we're interested in the acceleration, okay? So, the base is moving. We assume that the base is moving with a displacement of y of t from some reference configuration, reference point. And here the reference point that we're dealing with is going to be the equilibrium position of the mass of the casing. In other words, you put this thing, you mount it on the base that you want to find displacement, for example. This mass is going to settle down to a particular location. So that location is the reference point that we're going to measure all displacements from. Okay? Now, let me remind you, this is a classical situation of a base excitation problem. Okay, we have done things like this without this voltage gadget, etc., where for example, the suspension of a car was going over a wavy road. So it was pretty much exactly the same problem, except that the base motion there assumed, for example, it's a wavy road, or here we're interested in the accelerometer aspect of this thing. Now, the free body diagram for this mass is put on the right-hand side. Okay. There is, of course, the spring force and the damper force, but these are defined, these are in reference to the relative stretching or relative velocity of the two endpoints. Because notice that this base y is moving. This mass m is also moving. So, for example, the relative stretching or the compression of the spring is just x minus y, because It is moving x, mass is moving x by the amount x, but the top of the casing, see that the casing is also moving by the amount y. So the amount of compression or stretching is just the relative displacement, which is x minus y. And by the same token, velocity is the relative velocity that we are referring to. It's x dot minus y dot. Okay? By the way, as the mass moves inside of this casing, its relative motion is defined by the voltage, by this voltage divider gadget. Because if you know the voltage across these two points, then for example the voltage between this location and the top pole is coming from the voltage divider formula. So this resistance divided by the total resistance times the voltage difference. So in a sense, the relative displacement of the mass inside of that casing is proportional to the voltage produced from this point to that point. Okay. Now this is the voltage source, which is fixed the battery, so that doesn't change. But the voltage between this point where the mass sits, that's location, and that point is coming from voltage divider. Therefore, we are no longer talking about voltage because that voltage will tell us what the relative displacement is. Now, this is the same free body diagram that we had about 2 weeks ago when we did base excitation. So write the Newton's second law, sum of all the forces is equal to mass times acceleration, and just clean this up in a minute. Now, let us assume for the derivation of the concept that we want to discuss, let us assume that the base is actually moving harmonically, okay? Now, it may not be a situation, but this is a very common occurrence. For example, hypothetically, you have a machine, that is an accelerometer is mounted on it, and the machine's motion is maybe based on a force on balance is harmonically. So what I'm saying is that, look, let us assume that y of t varies harmonically like that. Okay? So we can clean up after we put this thing back in there. And if we decide to use, instead of x that's up there, the relative displacement in terms of z, in other words, z is equal to x minus y, then it makes our job easier because this term is going to be z, this is going to be z dot, and then we clean up, write x dot in terms of y dot, and we write x double dot in terms of y double dot and z double dot, and we clean it up, we get this equation. Okay, good. So this is the equation that describes the dynamics of an accelerometer, a very basic accelerometer, old-fashioned accelerometer. These days you don't see things like this, but this is how things started in the first place. All right, it's called a generic yet classical accelerometer. Okay, let's move on. Now, notice that we have chosen to write things in terms of Z because it is actually, this voltage is actually indicator of Z, proportional to Z, okay? So for your reference, I've written it once again here, and we have, this looks very familiar to us because when we did base excitation on the harmonic loading, we got pretty much exactly the same kind of equation, okay? And we got the solution to this. So if we go back to our notes, we'll see that we have solved things like this many, many times, appearing in different ways. And the solution to Z is an amplitude. Here is the amplitude. And here is the cosine of the same frequency, omega b here, but there is a lag involved, okay? It's your differential equation, second year differential equations, okay, and that we have revisited in this course in the first 2-3 weeks of the development. Now, this is fine. There's nothing wrong with it. This is the amplitude that we call it big Z. This Y obviously is the amplitude of the base motion. We call it big Y. So the moral of the story is that we can clean up this big Z in terms of big Y by a little bit of massaging and writing things instead of omega n and omega b, writing things in terms of the frequency ratio, which is omega b over omega n. Okay, so big Z is the amplitude of the motion of the mass. This is big Z. And big Y is the amplitude of the motion of the base, wherever this thing is mounted on, this accelerometer is mounted on. And we can plot this as Z over Y. Now, you might say, wait a minute, I haven't seen a graph like that. Because when we did base excitation, we didn't actually plot we didn't plot Z over Y. What we plotted was big X over Y. In other words, when we did base excitation, we decided not to use the relative stretching or compression of the spring, but we used the absolute one, big X over. That's why the graph looks different. The graph looks different. And but here we are. So this is big Z over big Y. Okay, so there are two regions that are indicated here. One is for large values of R on this side. And notice that these curves, which is the ratio of big Z over big Y, become almost flat, kind of irrespective of what the damping ratio is. And they're equal to each other because this flat line is where big Z over big Y is equal to 1. And then there's a second region on the left, which is the accelerometer region. So, which is for relatively low values of R, below 1. Okay, we're going to concentrate on seismometer region first. So here's what we already know. And notice that when R is kind of on this side to the right of 3, okay, big Z over big Y is almost 1. That means big Z is approximately big Y. And that means that the relative displacement of the mass, inside of that casing is almost the displacement of the base. Okay, so the motion of the base as far as displacement is directly equal to, very close to, motion of the mass inside of the casing. All right? They have the same amplitude. Big Z is approximately big Y. Now, notice that this happens when R is roughly bigger than 3, in that range. And that means that the base frequency must be, in order for us to be able to use this observation, base frequency is bigger or equal to 3 times the natural frequency of the gas. Okay? So, assuming that we know omega n and zeta, the measured displacement is big Z. The true displacement is big Y. Okay? And they're almost equal to each other by this factor. This factor is very close to 1 when R is in that range bigger than 3. All right, so seismometers are used in places where we want to measure the displacement of something. We are not interested in the acceleration, we are interested in the displacement. And I'll show you some gadgets later on that actually you may be interested in that. For example, in the case of earthquake, you want to know how much the ground is moving vertically up, for example. You want to know the value, the amount of this displacement, okay? Let's concentrate on the low end of the R-axis. In other words, this range, something around R less than maybe 0.3, 0.2, something like that. This is called the accelerometer region because I want to show you something about what does Z reading actually give us here in the seismometer region. Pretty much Z gave us the value of Y, but you want to know what happens here. Okay, so we're going to go back to our original equation. This is true, irrespective of how things are. And notice that this R is omega B over omega n. By definition, this R is omega B over omega n. So I'm going to put omega B over omega n here for the top, not the bottom. The bottom, we keep it the way it is. It's just that this R on the top, I'm going to write it as omega B over omega n. So when you do that and you clean up, you get omega n squared times this thing, because remember, on the numerator, we have omega b squared over omega n squared. If you take this omega n squared to the other side, you get this. And now I'm going to take y to the other side, and we're going to get that. That looks kind of familiar. We have the harmonic motion of the base. Okay? If you take two derivatives of that, you get the same harmonic function back. For example, if little y was big Y times, just hypothetically, sine of omega bt, you differentiate it twice. You're going to get y double dot equal to omega b squared big Y sine of omega bt. Okay. The second derivative of sine is also sine. The moral of the story is that what you see there, this is the maximum acceleration of the base. This is the maximum acceleration of the base. And what it's telling you is this. Look, Z is approximately, or Z is proportional to maximum acceleration of the base. You might say, well, what happened to this omega n squared? Well, if I take omega n squared here, I get omega n squared dividing by this. This is the proportionality factor. See, if I take omega n squared on the side, Z is equal to, all right, this ratio, which is pretty, for over here on this side, you can see that, times that. So Z is proportional to that number. And what is the proportionality factor? It's omega n squared times this. And this number is the maximum acceleration of the base. Okay. Now, notice that so for small values of R, if R is small, this thing, small values of R, is almost the same as that through that proportionality factor. Because notice that when R is small, this is almost 1. You can use almost, all this thing is almost 1 for our small values. Okay, so and what we are reading, of course, out of the accelerometer is big Z. Remember, big Z, displacement of that mass, is proportional to voltage. So what we're getting out of the accelerometer is actually Z. It is not omega n squared z. Okay, so in order for me to be able to say what is the maximum acceleration, what is the maximum acceleration of the base, I not only need to know z, which I'm getting it out of the reading, the voltage reading, but I also have to know the value of omega n. In other words, the natural frequency of the accelerometer. Okay. Obviously, you're reading z from the voltage, but I better know omega n if I'm trying to find the maximum acceleration, okay? Because it's not only the z that comes into the picture. The maximum acceleration right there, is omega n squared times z. Okay, now, notice that the damping also plays a role here because close to the zero value, close to the zero R value, that ratio, that ratio 1 over square root of dot, that magnification factor depends on the damping ratio, right? You can see that. And notice that for the damping ratio of 0.7, what we said is pretty much correct. In other words, that damping ratio, that 1 over, not damping ratio, sorry, magnification constant, 1 over root of, etc., 1 minus r squared plus dot, is very close to 1. So 0.7 is the optimum level of damping in an accelerometer, okay? So this coefficient is very close. This is the proportionality coefficient, very close to the value of 1. If, first of all, R is less than 0.5, roughly 0.5, less than 0.5 right there, see that? 0.5. And for the damping ratio of 0.7. Because the damping ratio plays a role in this value. You can see there's a zeta sitting there. For zeta equal to 0.7 and R equal less than 0.5, this number is very close to the value of 1. You can see that flat. Okay. Now, to be on the conservative side, what we're going to do, we're not going to go all the way to 0.5 because if you go all the way to 0.5, you'll see there's a deviation from 1 here. This one is not the line. So we're going to say, okay, if damping is 0.7 and R is less than 0.2 right there to the left of 0.2, we almost have the value of 1. In other words, for the operating range of the accelerometer is R less than 0.2, or omega b over omega n is less than 0.2. Okay, or omega b is less than 0.2 omega n, and if you write it in hertz, you're going to get the frequency of the base in hertz is less than 0.2 natural frequency of the device. Okay. Okay. So generally speaking, gadgets like this, old-fashioned accelerometer like that, these are defunct, but they're very good for explaining things in terms of what you have learned in the last 3-4 weeks, is that the natural frequency of a gadget like this as an accelerometer is around 100 hertz. If I put 100 hertz here for FM, I get the frequency of the base motion meaning here the thing that you mount the accelerometer on, and you want to see the motion of that. It could be a bearing or it could be a machine, etc. is less than between 0 and 20. That's pretty low. 0 and 20 hertz. This accelerometer is useful only when we are trying to measure accelerations of the base here, base of the accelerometer between 0 and 20 hertz. That's a very restricted requirement. Okay. A lot of structures, most structures may be oscillating at higher than 20 hertz, and this is going to be useless for it. But in the modern accelerometer, instead of a spring, okay, and a voltage divider like that and a battery source, what they use is a piezoelectric material. Okay, in other words, instead of the damper and the spring, they mount something, a mass, on a piezoelectric ceramic. So a piezoelectric ceramic, when it's compressed, okay, it creates a charge, and that charge will dictate the level of the output in terms of voltage. Okay, and for such gadgets, piezoelectric accelerometer, then the natural frequency is about 80,000 hertz. So this Fn is 80,000 hertz. So that restriction will tell you that you can measure vibrations up to 80,000 times 0.2, which is 16,000 hertz. That's very good. Instead of 0 to 20, which is measured with stuff like this, you can measure between 0 and 16,000 hertz as long as you pay a price, go to a new technology, new material, ceramics, piezoelectric ceramics, and replace it from K and C to that particular ceramic block. Okay, major achievement. But I can tell you that 100 years ago, 80 years ago, 90 years ago, this was it. That is how an accelerometer looked like. So, if we know omega n and zeta, then the measured acceleration, which is coming from the accelerometer, divided by the true acceleration, which is what you're trying to measure, is given essentially by this expression. Okay, this comes out of the accelerometer. This is what we want to know. They have this relationship. If you know omega n and zeta, you know the right hand side. Okay, all right. So there's a few comments that I would like to make about accelerometer, piezoelectric accelerometers. I'm gonna go to read this thing so that you don't miss anything important. So here is a modern piezoelectric accelerometer. There is no damping. There is no damper. Let me put it this way. And also this provides some kind of a stiffness. It could be that this K, in certain design, this K is actually, embedded within that piezo ceramic. Okay, so more or less universally used these days, and it exhibits much better all-around characteristic for all type of among all type of vibration transducers. Okay. Now, it works over a wide range of frequency, and remember 0 to 16,000 is a wide range of frequencies, and a very good linearity. Linearity is something that's highly desirable in instruments, okay, experimental gadgets, okay, and basically it's fairly stable over a long period of time. Okay, they do not need a power supply because the squishing of that piezoelectric material will create a voltage. Remember, in that generic and old-fashioned accelerometer, you had to attach it to a power supply because it was based on voltage divider formula, so you need a power source. That is not the case in the case of piezoelectric accelerometer. Okay, there are no moving parts. Okay, this mass, yes, it is. You can think about it as moving, but it's pressing against this ceramic. Okay, and this is different from having literally a main moving parts. Okay, so when you squish this thing, either intention or compression, it generates a voltage. Now, generally speaking, piezo ceramics must be in compression. So even if you have a situation like that, you pre-stress it through a stud mounting so that it's always in compression. So if it ever goes into tension, there's already a pre-compression in it, so it doesn't completely become free. Okay. Now, it essentially the voltage developed by this piezo ceramic is proportional to the force that's applied to it to squish it, and we know that force is the mass times acceleration of this little m block. Okay, so you're squishing this piezo with a force F. That force F comes from the vibration of the mass. So if you look at it, that F is internal force between these two pieces. So essentially we have a mass with a force, and the force comes from acceleration of the mass, this big M, this M, and through Newton's law. Okay, we're going to do an example in a minute. With that, hopefully that becomes more clear. Before I do the example as mentioned, I would like to go back to this slide and notice that it says, assuming that you know the characteristics of your measuring device. In other words, if you know your omega n and zeta, and the measuring device is that rudimentary thing that I showed you with the casing that we're analyzing, then and assuming it's used as an accelerometer, then we know that the measured acceleration or the true acceleration is given by the right-hand side. Okay, now remember, that gadget does not give you directly the acceleration. Okay, it'll give you the displacement. It gives you a voltage that's proportional to the displacement, relative displacement. So in order for you to find the measured acceleration, you have to take that data multiplied by natural frequency squared, and that the requirement is that, of course, you know the value of omega n. Okay, and also remember that the damping ratio has an effect, and the optimum one that I showed you in those graphs was 0.7. So that's why it says, assuming that you know the characteristic, omega n and zeta. So the next example shows you how do you go about finding omega n and zeta if you don't have your data sheet when that information is recorded in. So let's go to that example now. Okay, here's my example. Now, in order to get your omega n and zeta, you need another independent measurement of the acceleration. Okay, so some other gadget, either another accelerometer that you knew the data, whatever, you used it to come up with the quote-unquote correct acceleration value. So you need an independent measurement of the acceleration. Now, suppose that we are using an accelerometer to measure the oscillation of an airplane wing caused by the engine rotation at 6,000 RPM, which incidentally is 628 rounds per second. Now, suppose we are told that somebody else made measurements of the acceleration and they came out with 9.81 meter per second squared. Now we want to know the characteristics of our device. So suppose we used our device and came up with 10 meter per second squared. They gave us 9.81, with another device, and we pretend that that's the correct value. Now we do use our own device and come up with 10 meters per second squared. Out of this information, we want to estimate omega n and zeta. Okay, let's give some information about our device. It has a 0.01 kilogram mass in it, okay? So that's 10 multiplied by 1,000, that's 10 grams. And it has a damped natural frequency of 100 hertz. So our device has a damped natural frequency of 100 hertz. Now, how do we get information about damped natural frequency? We use, for example, a free vibration, okay? Record the data. Based on the recorded data, we calculate logarithmic decrement, and from the logarithmic decrement, we're going to get our damped natural frequency, okay? Actually, to get the damped natural frequency, you don't even have to do the logarithmic decrement. That is not needed. If you just want the frequency, you just look at the plot of the plot generated, for example, on the oscilloscope or whatever of your device, which is freely oscillating, and you get a graph, and the distance between two peaks is the damped natural frequency. Okay. Now, out of these two pieces of information and what we're told here up here from an independent source and what we did, we want to estimate the value of omega n and zeta, or get our C and K. Okay. So here's what we have. Measured acceleration over true acceleration is given by this right-hand side. So we measured it, and we came up with 10, and somebody else gave us the data, and we put our blind trust in them that their value is correct, 9.81, equal to the right-hand side. So there we are, 10 measured by us, 9.81 measured by somebody else, and we pretend that that's the correct value, equal to right-hand side. Now this will give you one equation, two unknowns. There you go. This is one of our equations. We need another equation. So that other equation is based on the information about the damped frequency. We are told that our damped frequency is 628. Okay, 628. So what we're going to do is going to write down omega b or omega d. That omega d is our 628 that we were told in the last sentence of the problem statement. Now, as far as omega b over, as far as omega d is concerned, we know what it is. Omega n square root of 1 minus zeta squared, right? That's what omega d is. Omega d is right there. Now, notice that we have omega b over omega n. Isn't omega b over omega n just R? Omega b over omega n is just R. Frequency ratio. Square root of 1 minus zeta squared equal to, we know that our omega b was given in the problem statement. The engine is running at 628 rad per second. We were told that our damped natural frequency is 628. So this ratio is 1, okay? This was the engine speed. This one is based on our experiment that we did. We found out the damped frequency, damped frequency is 628, okay? So remember, that plot that I was talking about gives you damped period, and you convert it to frequency, you get 628. So here's our second equation. Equation 1, equation 2, two unknowns, R and zeta. So this, if you take this R and stick it in there and solve for zeta, you get two values. Now this one is no good because this is the overdamped situation. We're talking about oscillation. So our zeta, the zeta for our device is 0.56. And of course, you know the value of R. Plug in zeta in here, you find the value of R. And once you find the value of R, you can find natural frequency by definition. Okay, we have the stuff down here. We have omega D628 that was given to us. That's omega n. And once we have our omega n, because we know the mass of our accelerometer that was given to us. Okay, we can plug it in here and we get our C value. Remember, the whole thing was, what is the K? What is the C? We just got the C, okay? And K is just m omega n squared. There we are. So here's what happened. We had a measuring device. We knew two things about it. We know its mass, and we know its damped natural frequency. Of course, that damped natural frequency can be coming from recording the data over a free vibration and finding the damped period. They'll give you the damped frequency. So we had the mass and the damped frequency. That's number one. Then we used it to find the oscillation frequency of a vibrating wing. And we came up with 10 meters per second squared. Somebody else gave us his or her damped frequency or not damped frequency. Somebody else gave us the acceleration measured by his or her device and came up with 9.81, and we pretend they know everything. We pretend that's the true value. So out of these, we calculated characteristic of our device, namely the C and K of our device, which incidentally means that omega n and zeta of our device. That's what the problem was about. Okay. Now, before I move on, I want to tell people that this business of seismometer was actually developed in China about 2,000 years ago. So that fellow that you see his picture on that Chinese stamp is the person who actually invented this device. Now, it's hard to predict. It's impossible to accurately predict the earthquake, but once it comes, then you can measure the displacement of the ground through this device that the fellow developed 2,000 years ago. Now, these days, the old-fashioned way of that 2,000-year-old gadget is you have a mass, you attach it to a spring, and you have a piece of paper that's round around this disc, which is rotating, the cylinder that's rotating, and the whole thing is mounted on the ground. If there's an earthquake, the base moves up and down. It makes this mass to vibrate up and down, and it records the displacement. Now remember, under certain conditions, this displacement that you get is precisely the displacement of the base, and we discussed that in the seismometer section of this lecture. Okay. Now, one other thing that I wanted to mention to you is that if you look at the development of seismometer at the first 10 minutes, 15 minutes, we said that it's in the range on the right-hand side where R is very large. And if R is very large, you can think about it as omega n being very small. And if omega n is small, look at the formula for omega n, root of k over m. M is very large. So seismometers have usually large masses. On the other hand, the other end is accelerometer, where R is small, right? In general, look at the section of the graph, which was accelerometer region. R is a small. If R is small, that means omega n is large. And once again, look at the formula for omega n. It's root of k over m. If omega n is very large, m is very small. Small mass inside the casing, inside the gadget that sits in your cell phone to measure acceleration. Okay, small mass, accelerometer range, large mass, seismometer range. But anyway, let's do a problem here. It says the seismometer has a natural frequency of 4 rad per second, so there is your omega n, and we have a damping ratio of 0.2. Now these are not hard to come up with because you do logarithmic decrement and you find out what the zeta for the gadget is, 0.2. Okay, is mounted on a structure which is vibrating sinusoidally, harmonic. You can pretend it's either the ground. Well, ground obviously is not going to be earthquakes, not doing the harmonic loading, but anyway, it's sitting on a base that is harmonically loaded. Okay, now if the peak to peak recorded data is 8 millimeters on this seismometer rotating paper, okay, then big Z, of course, is 4 millimeter. Find the amplitude of displacement of the structure when the frequency is 40 rad per second. So if the ground moves at 40 rad per second, okay, what is the amplitude of the motion of the ground, assuming that on our seismometer it shows 4 millimeter? So remember, for seismometer, measure displacement over true displacement. We don't know the true displacement, but we know the measured displacement. This big Z is 4. We're going to use it later on, okay? And now we are told that the ground is moving at 40 or, yeah, 4. The thing that's moving harmonically is 40 rad per second. We are told the natural frequency of our seismometer is 4. That'll give you the value of R. That's good because this is a large R where seismometer is applicable. This formula is applicable. So we are told that the measured displacement is 4 millimeter. We don't know the true displacement of the base that it's sitting on. Okay. And just plug in the value of R, plug in the value of zeta, and that'll give you the value of big Y. And that was the question. All right. You should also be familiar with the terminology of active vibration absorber versus passive vibration absorber. Now, you don't have to be a genius to realize that if you're sitting on earthquake in an earthquake region and the earthquake takes place, uh, this building sways back and forth, okay? And of course, it also goes up and down, we know that. But as I said, you don't have to be genius to realize that if 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 you put springs underneath this building, it'll give it the ability to swing back and forth easier. And basically, these springs act as the vibration absorber. Okay, it's smoothing out this destructive force. Now, this is fine, except that there's also the concept of uh, active. This is the passive one, the one that just sits on that just sits on springs, dummy springs, is called the passive one. But the active vibration absorber is when you actually intentionally add some damper to work in unison with those springs and basically reduce the motion of the building. Okay, either up and down, sideways, depending on what you're doing. So in the active vibration absorber, you interfere with the system through a damper so that things look better. We will do one lecture about the vibration absorbers later down the road towards the end of the semester, but anyway, that's it. Okay, the next few slides are taken from Dr. Novak's material published from the NVH research group. And I think you're going to find these things useful. So the first thing I want to talk about is this decibel scale. So when you look at this legend that you see here, on a very calm day, nothing happening, the level of acceleration can be thought of as pretty much none, 0.00, basically 10 to the minus 6 uh, meter per second squared. Okay. When there is, if you look at the washing machine, for example, the level of acceleration can be associated with 1 meter per second squared. During an explosion, a very violent event, the acceleration can be associated with it as 1 million. Okay. Now, so this is a reference, nothing happening. This, for example, a doomsday situation, and we can define a decibel scale associated with these events. And one way of doing it is, for example, say 20 log of acceleration in g of the event that you're interested, divided by acceleration in g of some reference situation. And if we take a reference situation to be the very bottom case on the left side, then it's 10 to the minus 6g. Okay. Now, if you look at the scale and you plug in, for example, a million meter per second squared in that expression, obviously the g's cancel out, and you're going to get log of 10 to the 6 divided by 10 to the minus 6, okay? And that is going to be, work it out, you're going to get 240, okay? Because it's log of 10 to the 12, log of 10 to the 12 is 12, 12 times 20 is to the 40. So the decibel scale, according with the intensity of this acceleration, when the very bottom left corner is taken as reference, is this. Now, for example, if you plug in this level of acceleration, so notice that here you're going to get 10 to the 6 over 10 to the 6, and log of 1 is 0. Okay, so instead of referring to these levels of acceleration, you can refer to it in the decibel scale, assuming that you have taken this as your reference situation. Now, in general, this does not have to be in terms of acceleration. It can be about any entity, x, and we can associate with it a reference entity, okay, and then we discuss these values of x in terms of the decibel scale. Okay. Yeah. So you can see here on the left side you have the acceleration. On the right side you have essentially the same thing but in a decibel scale. All right. The other thing I want to mention is that when you take one of these accelerometers or transducers, I mean, basically you start with a transducer, a gadget, like the very generic one that I showed you for the mass spring damper system in the casing with the base moving and there's a voltage source, etc. Well, first of all, there's a lot of steps that goes from this end to what you can actually look at the output on your screen, etc. Among them, for example, the level of the voltage can be so minute that you really have to magnify it considerably, and that's a preamplifier stage. And even then, there's a lot of noise that may be coming into the picture that has to be filtered out and sorted it, okay? And finally, it goes through another intermediate stage, and all the way to your output. Okay, so there's a lot of electronics built in here, going from a transducer all the way there, and many of it is outside the scope of a course like that. In fact, they belong to different subjects. For example, uh, signal conditioning and digital signal processing, etc. That are important, but we have no interest to discuss such things in the present course. The other thing is you have to remember that piezoelectric is a major ceramic was a major breakthrough in this whole business. Piezoelectric ceramics are gadgets that or material that when deformed, they produce a voltage, or the other way around. Could be the other way around. You apply a voltage, they change shape too. Okay. So here, for example, you can see that if you have a piezo ceramic and you compress it, there's a voltage produced across the two poles here. Or even if you shear it, there is a voltage produced. So this was a major breakthrough in going from the traditional or the mass spring damper system into a more sophisticated one. Of course, the signal processing, and all those things that I described in the previous slide, they also apply here. It's just that this is the transducer stage. Now, the piezoelectric accelerometers come in different varieties. For example, they're all very small, as they are in all accelerometers, because M is 0. Remember, omega n is very high. And here they're showing you, I mean, 4 different kinds. The piezo material is built in here, like this red stuff here. P, it says P. These red panels, these panels, the piezoelectric crystal material. The springs are, for example, notice that here these this red, this yellow flat panel on the top. That's where the spring is built in by different ways. You remember you can compress the piezoelectric because that is really the mode that these ceramics operate on, the compression mode. Okay, and then there's the base, of course, and there is the electronics. As you can see, electronics actually right here. There's electronics built in. So there's a lot there. I'm not an experimentalist. I'm not in the business of designing these things, but it is important for us to know some of the variety of different piezo transducers that come in. Now, any transducer will have a data sheet associated with it, and the data sheet, for example, it gives you graphs like this, but actually tells you what the natural frequency of it is, and depending on the type of motion, depending on the type of mounting of the transducer and the base where it's supposed to measure something from, can be, for example, beeswax, okay, just something very sticky between that and the transducer, between the surface and the transducer. It can be cementing stud, okay. It can be mounting, like a screw type thing, stud mounting here, and double adhesive tape. You can see that the behavior is pretty much the same, except that the natural frequency of that gadget can be different depending on it reveals itself as a different number. Okay. Now, as far as the mounting of these goes, you have to put it on the right spot. For example, if you're interested in the vibration of a machine, it has to be mounted. Probably you're interested in the machine itself, not the casing of it. You have to mount it on the bearing situation. Okay, so don't mount it on some thing that is not of interest to you. Don't mount it on the shaft, don't mount it on the casing of the machine, but on the uh, proximity of the bearing. You can see that. So the bearing, ball bearings, okay? And yeah. Now, there are certain conditions that can affect the operation of the performance of the transducers. For example, if you have flat, instead of flat surfaces, you have curved surfaces, there's a base strain that can cause a problem. Humidity can dramatically affect the performance of a transducer here. And acoustic noise can affect them. Corrosive material, the presence of a magnetic field can affect the results. And of course, nuclear radiation, that we don't want to go there. Now, here is an example that I've taken out of this IIT work. And they realized that for their tractor, for a certain tractor, the steering wheel was dramatically affected by the vibration of the idle condition. Okay, now it's obvious that the resonance, the natural frequency of this steering wheel match the operating condition, and you have to basically redesign this so that you eliminate the possibility of resonance. So what they did is, in this particular problem, they took a we can change the mass of this, obviously. Delta drifted away from their resonance condition, or you can add uh, uh, rigidity to it. You can increase the stiffness by adding another bar here, and that'll take care of it. So that's a good example. I suggest you look at it when you have a chance. And that wraps up the lecture 13. Now, I have to admit that I'm not an experimentalist, but these are so critical, and I strongly urge you, if there is a possibility of taking a vibrations course which is geared toward experimental work, you look it up and consider it seriously. Of course, what we're doing here is a very basic, elementary, the fundamentals of vibrations, and you need more than that. Good luck, folks.